In this video, I am going to solve partial differential equation by using variational iteration method. We have this partial differential equation over here, and we have two conditions on u. One is for y is equal to 0, which is x, and another condition is u of 0y is equal to minus y. So what we do, we first write the correction functional of this problem. And from the theory, we know that the correction functional is written like this: un plus 1, un plus, remember that un is a function of x and y, plus 0 to x. Then we have lambda partial by some derivative of that, some quantity un, and here we need to decide where we can apply the correction functional. For example, we have partial u by partial x, and from the theory we saw that if you have x, then you can replace this with xi. So what we do, we also replace this partial u by partial x with partial un by partial xi. It means that un will be a function of xi and y. Then we have a modified problem minus partial un tilde over partial y and minus 2, which is acting as a non-homogeneous term, that will be equal to dxi. Integration is with respect to xi. So that's how we write the correction functional equation. This is called correction functional problem. Now, what we do, first we need to understand what is lambda over here. Since our linear operator is partial u by partial x, although partial u by partial y is also linear, but we are interested in only one linear operator, since according to the theory, when we have first derivative alone, then lambda is equal to minus 1. If we have, for example, minus partial u by partial y, two linear operator, only one linear operator, but there are two, for example, then lambda will not be equal to minus 1. So we decide partial u by partial x as our operator. And this partial u and tilde by partial y will act as a modified solution, which means that delta u and tilde is approximately equal to 0. It is very small, so we neglect that. We actually write this u and tilde, but when we solve it with this keeping u and tilde in the calculation. When we have n is equal to 0, we get u1, u0 plus, and we already decided that lambda will be equal to minus 1. Either it is for first order ordinary differential equation or partial differential equation. So when we put lambda is equal to minus 1, it becomes 0 to x. Then we have partial u naught partial xi y divided by partial xi minus partial u naught partial y, u naught is xi and y minus 2 dxi. Remember that we, although shown that this is u and tilde, but this is only for the theory. In the theory, we have put it this equal to 0, but in calculation we use this calculation over here. We use this term in a calculation. So u naught, the initial guess will be coming from this equation, ux0 is equal to x. So u naught will be equal to, I'm sorry, I have to look at not from this initial condition, this initial approximation, but from here. Since we are putting, we are taking linear operator with respect to x, so the condition should also come from this condition. So this becomes u naught xy u of 0y is equal to minus 1 minus y. That will be our initial approximation. We put u naught over here. This becomes minus y minus 0 to x partial by partial xi u naught xi y, that will be equal to minus y minus partial by partial y u naught xi y is minus y minus 2 dxi. So from here we get minus y minus 0 to x. Since there is no xi, this will be equal to 0 plus, then we have 1 minus 2 dxi. And from here when we solve this problem we get minus y plus x. This is u1. Similarly, I leave this to you to find the second solution. N is equal to 1. N is equal to 1. We get u2 is equal to u1 minus 0 to x partial by partial xi u1 xi y minus partial by partial y u1 xi y minus 2 dxi. So then we get, after putting the values from the previous iteration, we get minus y plus x minus 0 to x. What we do, we replace this x with xi, this with xi, this with xi minus y plus xi, then take a derivative with respect to xi. So we get from here 1 minus, and the derivative of u1 with respect to minus y, that will be minus 1. So we get plus 1 minus 2 dxi. So 2 minus 2 is 0. So we get u2 minus y plus x. So it means that when we have a solution minus y plus x, it will continue like that. And for n is equal to 2, we get u3 minus y plus x, so on, so on. So it is actually repeating itself even after many iterations. So our solution is limit n approaches to infinity un, that will be equal to u, and that solution is actually minus y plus x. U is equal to minus y plus x. If you just want to verify that either this solution is correct, so what we do, we take left hand side partial u by partial x minus partial u by partial y minus 2. On the left hand side, partial u by partial x is 1, partial u by partial y is 1, 1 plus 1 is 2, which is equal to right hand side. So you can see the beauty of this variational iteration method, which is giving you the solution in a very decent way. Otherwise, if you solve this problem from the methods that you probably learned from the PDEs, it becomes very tedious in that case. For that case, for example, you apply the method of characteristics, maybe you can apply, or maybe separation of variable, Fourier transform, Laplace transform, so on and so forth. You can apply many other methods, but in this way you get exact solution and in a very decent way. So let me just solve another problem, and I solved that non-linear problem. So then it becomes very interesting. So our problem is example, solve by VIM, variational iteration method. We have partial u by partial t plus u partial u by partial x is equal to x. Okay. So this is our equation number 1. We also have initial condition ux0 is equal to 2. This is our equation number 2. Now in this equation, if you want to identify the linear operator, you have only one choice, that is partial u by partial t. It means that you have to write your correction function and lambda for this operator only. This is the nonlinear equation. So what we do, we get the correction functional problem as un plus 1 is equal to un. Remember that here un is a function of x and t, and on the left hand side we also have x and t. So we have plus 0 to t lambda xi partial un xi t by, we replace this t with the xi, so we get partial by partial xi plus un xi t partial un xi t by partial x, and we have minus x dxi. So you can see that this is our correction functional. And remember that we also need to treat this as our zero variation function. Okay, but in calculation we will use that. So since our lambda is lu n is partial u n by partial t, in that case lambda is minus 1. We solve this problem, and we also see that our initial guess is equal to 2, and this is our initial guess over here. We put n is equal to 0, then we have u1 u0 minus 0 to t. Now you can also see that here you have used t as a, you have put it the value for t, then your limit is also from 0 to t, since you are replacing t with some xi. So minus 0 to t partial u0 by partial xi. Sorry, there should not be a t. It should be a, since x and xi. This is a correct way. X and xi. X and xi. Since we are so habitual of putting x is equal to xi, so I put it the wrong x xi. It should be x xi. Okay, so it should be x xi plus u0 partial u0 by partial x minus x dxi. We put u naught is equal to 2. When you put u naught is equal to 2, this is 0, this is 0, and we get 2 minus 0 to t minus x dxi. So we get 2 plus x, since x is a constant, we are integrating this with respect to xi, we get t, so that is 2 plus xt. Next we have for n is equal to 1, we have u2 u1 minus 0 to t partial u1 by partial xi x xi, replace t with xi, plus u1 partial u1 by partial x minus x dxi. u1 minus 0 to t, take a derivative of u1 with respect to xi, replace this t with xi, 2 plus x xi, so we get x plus what is u1? u1 is 2 plus x, t will be xi, partial u1 by partial xi, that will be x minus x dxi. Okay, dxi. So we solve it further. After solving it, we get u2, which is equal to, you can solve it yourself. You will get 2 plus xt minus t square minus xt cube by 3. Similarly, what we do, we put n is equal to 2, and then we have u3 u2 minus 0 to t partial u2 by partial xi plus u2 partial u2 by partial xi minus x dxi. We put the value u2 over here. You can see that it is a bit complicated, but you can try it and solve it maybe in 1 hour or so. So you will get at the end, I just write direct answer, 2 plus xt minus t square minus xt cube by 3 plus 5t raised to power 4, 12 plus 2 by 15 xt raised to power 5 minus 1 by 18 t6 minus xt raised to power 7 by 21, so on. So that is a bit complicated, but if you want to try it, you can try it yourself. And from here, what is the reason that you have written this u3? The reason is that we want to make a formula from that. So the formula for this is un. First, you need to define un xt. You can see that 2 plus xt, you can take common x from all these terms, x from here, from here, from here, and from here. And without x, we have these terms all together, something like that. So when I combine it, I get 2, 1 minus t square by 2 factorial plus t4 by 4 factorial minus t6 by 6 factorial. And nth term I cannot write for the time being, so what I do, I apply limit n approaches to infinity. When I approach n approaches to infinity, we get this term plus x. Then we have t minus t3 by 3 factorial plus t5 by 5 factorial minus t7 by 7 factorial, so on. So this becomes a Taylor, some functions Taylor series. So we get 2, for example, secant hyperbolic t plus x tangent hyperbolic t. You can find that yourself. This is actually a Taylor series of secant hyperbolic t. It is not a very common function uh, to have it, but this is a Taylor series of secant hyperbolic and tangent hyperbolic t. You can also verify yourself either this is a solution of over given equation, partial u by partial t plus u partial u by partial x is equal to x. So you can prove that. If first I should write the solution, to secant hyperbolic t plus x tangent hyperbolic t is over solution. So you can, I think you can do it yourself. Take left hand side, partial u by partial t plus partial u by partial x. Solve it, take a derivative with respect to t, then take a derivative with respect to x, then when you can add it, you get the right hand side. Okay, so I think you can do it yourself. So this is our solution. So here we finished finding the solution of non-linear partial differential equation and linear partial differential equation. Thank you for watching.